Hi everyone, my name is Andrea Husseini and I'm a lead product manager of Deltaflow here at Reveling. And today I want to show you a demo of how our Deltakit and Deltaflow products work together to enable real-time quantum error correction, which is essential to make fault-tolerant quantum computing useful. Let's go. To make quantum computing useful, we need quantum error correction, and we need that to be both fast and accurate. That's where the QEC cycle comes in. During computation, qubits are continuously read out, and this data is sent up into a decoding system such as Deltaflow. Deltaflow is decoding this data and issuing corrections back to the control system and the real qubits whenever necessary. The faster we can execute this entire cycle, the more operations a quantum computer can execute per unit of time. And the more accurate we are in decoding those errors, the longer we can sustain a logical qubit in time. So let's see how you would write a circuit on the joint system. You can write your circuit in Deltakit, which is our open source software platform for circuit generation, simulation, and analysis. That circuit is then passed to Deltaflow tools. This is where instructions and configurations are generated. That program is then executed on the control system with Deltaflow connected directly to it via the quantum error correction interface. Deltaflow is in charge of all data routing, data processing, and decoding. First, we're going to define the experiment that we're running, and we're going to use Deltakit for that. In Deltakit, we defined a rotated surface code of distance 3, which allows us to encode one logical qubit using 17 physical qubits. Deltakit also allows us to pick the number of rounds and the number of shots we want to execute the experiment for. Next, we need to inject noise into the circuit. This will allow us to simulate what the circuit would look like on a real device and also understand which errors are most likely to happen. Next, we need to connect to our real-time QEC system, Deltaflow. We need to tell Deltaflow about the experiment we're going to run so it knows what data to expect and how to decode it. A key part of this configuration is the decoding graph. The decoding graph tells us what the errors look like, represented by edges, and what checks will light up when we see those errors, which are the nodes. Since we don't have a full quantum computer available for this demo, we're going to be using an emulator. Our emulator is initialized here, and it's implemented fully in hardware. Then we're going to use this emulator and send all of those configurations over the quantum error correction interface to Deltaflow. And all of the data format and the specification is available for anyone to use. And finally, we're running our experiment, and we can see from the results that the decoder managed to get the logical error probability down to just 2%. This is a great result because it shows that our decoding is accurate, hence sustaining the logical qubit for a long time. But that's not everything. We also need to talk about the latency. We can see in this experiment our latency is well below 7 microseconds, and the entire distribution is well below our near-term target of 20 microseconds. Everything that comes into that latency is shown here. So all of the data processing, data routing, decoding, and sending the result all the way back into the control system is included. If you'd like to know more about our vision for the future of quantum error correction, head to our website to download our newest technology roadmap.